last 20 minutes or so of class. So our class is done at 20 after 2. So if it's getting pretty close to 2 and I'm not wrapping it up, and it seems like I'm just going to keep on going, somebody wave at me and say, you might be forgetting something. So let me know. All right. So we're going to be moving into a new concept, but it's not really that new of a concept. This is called Derivative Skills 2. We just did a couple of days of Derivative Skills 1. So the good news is, if you remember what the derivative of sine is, that will very much help you here. If you remember what the derivative of e to the x is, that will help you here as well. So it's kind of hopefully a natural progression from those Derivative Skills 1 into Derivative Skills 2. And today we're going to be looking at something called the chain rule. So I've got a little demo here that I wanted to show you guys. It's should be live here. There we go. I'll just do this one right here. So this is a GeoGebra demo. It's pretty awesome, but you can't see it. And now you can. So this GeoGebra demo is essentially a tangent line calculator. So if you can see here, I've got this set up with my function being e to the x. So can you all see how that black curve on the graph, I'll highlight it for you, looks a lot like e to the x. So I'll highlight it with this. E to the x, right? All right, and then can you guys tell me what the point of tangency is? 0.997. Yeah. So I tried to get the point of tangency really close to x equals 1. It wants to jump over that value. So it's almost x equals 1, comma, about 2.71. Does that make sense? And look what it does. It generates this lovely tangent line, kind of in point slope-ish form, right? They've added the y value over. And this will generate, it's kind of cool, really. This will generate a tangent line equation for any of these values. So you could like click and drag, and you can see that tangent line changing and its equation changing, so on and so forth. Kind of a cool demo. Does that make sense? And the blue box here is just a zoom. You can zoom way in, way out, whatever, and get a better picture over like on the right side. Does that all make sense? Okay. So I'm going to go back to that 0.997 for my x value right about there. Okay, there we go. So if we looked at this tangent line right here, we pointed out the point of tangency is 0.997 comma 2.71. What's the slope of the tangent line? Or you could say what's the slope of the curve right there? 2.71. Yeah, 2.71. Where are you getting that from? There's a bunch of 2. Which 2.71?
The tangent line equation above.
Yeah, but which?
Parentheses.
The one right by the parentheses. Yeah, so we're getting that tangent line slope from right there. Does that make sense? Okay. So you notice, and maybe you notice how the y value exactly matches the slope. And isn't that because the derivative of e to the x is just e to the x? I mean, hopefully that makes sense. So I thought what I'd do here is change this a little bit and see if I could get a prediction from you guys. What if I came down here and instead of e to the x, you see the highlighted in blue, I'm about to change this. Instead of e to the x, what if I made it e to the, bless you, e to the 2x? Now I got to hit enter for something to change here. So let's think this over. I changed it from e to the x, now it's e to the 2x. The slope of e to the x right there is 2.71. So my question is going to be, how do you think the slope is going to change? Is the slope going to change at all? What do you think about the relationship between the y value and the slope? What do you think that 2 is going to do? Any thoughts?
Double the slope.
Double the slope. Okay. What else? It's a reasonable conjecture, isn't it? Well, anybody think anything different? Or maybe you agree with him, but you think there's more. Maybe there's more to talk about.
Would it also add to the slope?
It would double the slope and then add something more to it? Okay. What else? Anybody else have a thought? This is purely conjecture, right? So there's not really a right or wrong answer here. I'm just asking you to kind of like play with this in your mind and think, okay, 2x, what would that do to the graph? What would that do to the slope? Quadruple it, okay? So you've got double the slope plus a little more, quadruple the slope. What about the relationship? Do you think the 2x is going to change the relationship between that y value and the slope? Like right now, the y value is 2.71 and the slope is 2.71. Do you think that, putting the 2 in there, do you think that's going to change that relationship, or do you think the y value and the slope will still be the same? Change the relationship? Okay. Are you ready to see? I'm ready to see. Let's check this out. So when I hit enter, it should accept the equation and we'll see. So is the slope doubled, quadrupled, doubled plus a little more? What's the relationship going to do?
Wow.
So what's the new slope?
14.26.
Yeah. So the old one was 2.71. So gosh, 2.71 compared to 14.686, that's a lot more than doubled. And it's actually closer to quadrupled maybe, right? Interesting. So you can take your calculator out and you can figure this out. Why don't you do 14.686 divided by 2.71? See if that really is quadrupled. Maybe Merrick was just close, or maybe he was just about right. Or maybe it is just doubled plus a little bit more, because it's clearly more than doubled.
You were right. That's 2.
Is it quadrupled?
No, it's like 5.5.
5.5? Okay. That's interesting, right? Like, where does this come from? And has anybody noticed the relationship between that y value of the point of tangency and the slope? Remember before it was 2.71 and 2.71. It was the same, wasn't it? What's the relationship now? It's actually relatively easy to see.
E to the x times 2.
Say again?
Oh, it's the slope is double the y value.
Slope is double the y value. Interesting, right? So I made that e to the 2x, and by the slope got multiplied by over a factor of 5, didn't it? But the relationship, there seems to be a connection there. So let me ask you this. What if, instead of e to the 2x, what if I decided e to the 3x? Now, it's kind of a mystery as to what that's going to do to the slope, right? Because before it was like 5.5. We seem to see a pattern here. What would you guess the relationship between the y value and the slope would be?
Y value is 1/2 the slope.
Y value is
Oh, it will be 1/3.
1/3. Okay, so it's a relationship of a factor of 3. Okay, let's see if that's the case. 19.897, 59 point. So it's basically almost 20 versus almost 60. Seems to be holding, doesn't it? About 3, isn't it?
It is about 3.
Okay. So then if we continued on with this conjecture, wouldn't you guys say that maybe if I did e to the 4x, what do you think the relationship would be?
4.
So roughly 54 compared to 216. It's a factor of 4 about, isn't it? So we're starting to see that as I change that function, but whatever that number multiplied by the x is, that's how the y value and the slope also relates. Kind of interesting, I think. Yeah, mathematics is often trying to see patterns. And we've kind of discovered one, haven't we? I don't know what a puppy has to do with this, but whatever. So, what you've seen an example of is the chain rule. And you know what? I wasn't going to illustrate it this way, but I'll do this really quick. The derivative of, this is what we'll try to summarize this pattern. The derivative of e to the x is e to the x times 1. And you might look at me and say, why on earth would you put times 1? Stay with me. How about ddx of e to the 2x?
EX times 2.
This is e to the 2x times 2. So when you look at this, can you see why maybe the slope was double the y value? We're going to find out soon enough that ddx of e to the 3x equals e to the 3x times 3, etc., etc. We want it all the way up to 4. We could keep going. We see the same pattern. Does anybody have any idea where the especially the 2 and the 3, but even the 1 really, where are they coming from?
Next to X.
Say again?
Coefficient of X. The coefficient of X.
Okay, yeah, it's a little more than just the coefficient of x.
Factor of X.
We're in calculus, so think calculus-y.
The slope of X.
Say again? Isn't 2 the derivative of 2x?
No.
Yes.
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 Isn't 3 the derivative of 3x?
Yeah.
4 is the derivative of 4x. So this is kind of where we're leading into with the chain rule. And I want to do a little explaining with the chain rule. And I've got a little illustration I want to show you. And I think we'll be in pretty good shape. So check out this. So the chain rule has always been there. You just didn't always know it. The chain rule has always been there, just not always obvious. The chain rule will become apparent when we are differentiating a certain type of function. What would you guys classify e to the 2x or e to the 3x as? Like, what kind of a function is that?
Exponential.
Exponential. Keep going.
Continuous.
It is continuous. Compound. I'm not sure what compound.
What?
I think you're going for the right word.
I just can't remember.
Starts with comp.
Composition.
Composite. Composition. There we go. So if you are differentiating a composite function, so are you guys all okay with a composite function being a function that's been input into another function?
Yeah.
An example would be right there, right? F of g of x. Like the input for f is not just x, it's a whole other function, right? F of g of x. Bless you. So I'm gonna show you Newton's symbology, then I'll show you my little demo. Maybe we'll talk a little bit about Leibniz's, but we'll use Newton's mostly. So if we are doing, and I hope that the little exploration there will help kind of solidify this for you. If we're doing the derivative of f of g of x, here's what we get. It's f prime of g of x times g prime of x. F prime of x, or excuse me, f prime of g of x times g prime of x. So in our little illustration with the GeoGebra demo, that g prime, what did that g prime show up as in all those little examples I showed you? It wasn't the 2x, it was, no, that was actually this.
No, it was or E X or something X. What?
It was,
Is the word? Oh my God.
I'm actually looking for just a number.
2.
It was the 2 or the 3 or the 4, those extra factors that showed up. That's where those came from. I wanted to find something for you, and then I want to show you my little demo with the boxes. Are you guys all comfortable with this terminology? If I called f the outside function, and I called g the inside function? That makes sense, right? G is the input. So I'm going to do a little demo back here by Tyler and Jackson. Have you ever, this will help us a lot as we go throughout the year in a number of ways. It might seem a little silly at first, but I think it'll really help you. What I have here in my hand is a box, and you might have done something like this to a relative or a friend, but have you ever gotten maybe yourself a birthday gift or a Christmas present, and it's like this fairly good-sized box, and you're excited, and you're thinking to yourself, there's hopefully something really good in this box. It's my birthday, it's Christmas, whatever. And you carefully unwrap the box, and you open it, and what's inside? Another box, right? This silly joke of like big box, little box nestled in there, and you're like, thanks guys, thanks a lot, it's a box. And what do they say? Open this one, right? So it's a smaller box, and you're like, oh, there's something in there, right? And you open it up, and it might be another box, or it really could be the present, or it could just be another box. We could carry this analogy on for a long ways, right? Because there could be another box and another box and another box. I decided to keep it pretty simple. I finally got to the present. It's a little Santa full of jelly beans. Yay, right? But I want you to remember what we did here, and I want you to see the parallel. This is a really useful parallel. This will often help people get this. So when I see this box, when I first see it, I don't have a clue that there's another box inside, do I? So here's what I want you to think about. I would like for you guys to think about, in our little analogy here, I'm going to rewrite this here in a second. I would like for you guys to think about the outside function as being the big box. The outside function is is this. This is the big box, right? So, as I get excited and I'm going to open this box up, when I open the box, this analogy holds really well. When I open the box, this is like differentiating the box. This is me differentiating the big outside box. And when I open it, I look and I see, what do I see in there? I see g of x. I didn't know it was there to begin with. I open it up and I see g of x in there. So this is equal to f prime of g of x. This is me sitting here with an open f, and I see g of x in there. Right? So g of x is sitting in there. So what do? I pick this up. And I take it out. Now I know that the g of x used to be in there. And I take it out here and I open it up. What does opening the box signify? I'm doing a derivative, right? I'm differentiating. Now remember, this was g of x. So when I open g of x, I get... When I differentiate g, I don't get g. I get g prime. G prime. And here's how the analogy holds even better. When you're a little kid and you get into this situation, doesn't your excitement in a situation, doesn't your excitement multiply? Yeah. And you're like, it's a big box and you're pretty excited. And then you open up and it's another box and you're like, oh, I can't wait to see what's inside the little box. And every box that gets open, maybe if there was like 3 or 4 of these nested, wouldn't your excitement get a little more multiplied? And so that's why, in our little analogy, we take the original derivative of the big box and we multiply it times the derivative of the little box. And there's your chain rule. Does that make sense? I hope the analogy is memorable enough to where maybe even when you're doing your homework, you're like, oh, I just need to open the big box and then multiply times opening the small box. That's really all the analogy is for. And so we're going to do a few examples here in a minute. I'm going to hold off on Leibniz's symbology. I kind of feel like that might confuse you more than help you. It's good, but I feel like it might confuse you. So let's do a few examples here and see if this all makes sense to you. And I know we got about 10 minutes here before we'll get things all wrapped up. So I would kind of like to give you a chance to do some guided practice here with number 1. So I want to kind of question you and get you thinking about this a little bit. First of all, I want to present an alternative to this. Did y'all realize that even though number 1 is a composite, right? Do you see how there's a function inside another function?
Yeah.
You really don't have to use the chain rule here. Do you realize what you could do?
No.
It's not a very fun alternative. Doesn't 5x cubed plus 2x to the 150th, doesn't that basically mean that base times itself 150 times? So if you wanted to, you could expand this, 5x cubed plus 2x times 5x cubed plus 2x, dot. Do like an ungodly amount of multiplication, probably mess it up because I think we all would eventually mess it up, right? Myself included. And then you go turn by turn by turn with a bunch of power rules, right? Can you see why the chain rule is far superior to that? We're going to be done in like 10 seconds. Okay, so check this out. With the chain rule, you want to identify the big outside box. And isn't the big outside box, Carter's right, isn't that the 150th power? We're just going to say, the way I'm going to put it is, it's the big box is something to the 150th. Because I don't know what's inside the box yet, right? It's something to the 150th. And then the little inside box is right in there, inside the parentheses, 5x cubed plus 2x. So the way that I handle this, I'm going to say f prime. Now remember, using the box analogy, I can only see the 150th power box. The way that I differentiate the 150th power is this. I go 150 parentheses, 5x cubed, or sorry, I'm not going to put that in there yet. 150 parentheses to the 149th, right? Isn't that the derivative of something to the 150th? And I'm hoping that the present is in there, but then I open up the box, and instead of seeing my present, what do I see in the big 150th power box?
15x squared?
No, I see 5x cubed plus 2x. So I want to be super careful about this. I'm not going to open both boxes at the same time. I can only open the big box. And then once I see the little box, then I'll open the small box. So now I want to open that smaller inside box. So what's the derivative of the little box?
15x squared plus 2.
There we go, 15x squared plus 2. And now because there were only 2 boxes, I'm done.
Is that fine as our final answer?
Please don't do anything else with that.
Mr. Blake.
I'd have to check back in with you like 2 days later and see if you got it right. I don't want to do that. Okay. What do y'all think?
Good.
It's okay? Okay. So then, why don't you look at number 2? Number 2 says, find the equation of the tangent line to the graph of y equals sine of, do you see how it's sine of pi over 3x? Do you see how it's composite? It's a function, like the input is not just x. It's pi over 3x, it's composite. So at least see if you can get the slope of the tangent line. I don't know.
Could we solve it and not use the chain rule?
You have to use the chain rule. If you're looking for the slope of the tangent line, got to use the chain rule. This one, like, yeah, so number 1, you could just like multiply out the 150th power if you wanted to avoid the chain rule for some reason. Here, I don't know, could you do some trig identity and maybe sort of avoid the chain rule? Maybe? That'd be way more trouble than it's worth. Chain rule is far, far easier. Okay, so we're just looking at number 2, seeing if we can do a derivative, get an equation of the tangent line. Okay, so with number 2, let's do the easy part first. If we are trying to find the equation of a tangent line, what are the 2 things that we must have?
Point of intersection or tangency.
Point of tangency plus slope of the tangent line. I'm kind of thinking that the point of tangency, as long as we know the unit circle okay, that's going to be the easier one. So I'm going to say point of tangency over here. Wouldn't that just be y equals sine of pi over 3 times 2? Just plug it in the x value. So it comes down to sine of 2 pi over 3. What is that?
Square root of 3 over 2.
It's root 3 over 2. Good. So my point of tangency is 2 comma root 3 over 2. So I got my point of tangency there. I'll put that together with my slope here in a second. So I need my slope of tangent line. So I got to find my derivative. So I got to find dy dx. Now when you look at this, a key idea is we need to be able to recognize quickly, hopefully, that sine of pi over 3x is composite. It's not just sine of x, it's sine of something a little more than just an x. So because it's a composite function, we've got to use the chain rule. Can you guys identify the big outside box in this one?
Sine of x.
Sine, I usually say sine of something, right? Because I know the input's a little more complicated than just x. I'm going to say my big outside box is sine of something. And what's the derivative of sine of something?
Cosine.
Cosine of that thing, right? So cosine of blank. And of course, then we open that big box, and what do we see inside? Pi, the most wonderful gift ever, pi over 3x. So we see that in there. And then we open that, a.k.a. we differentiate it. What's the derivative of pi over 3 times x? Just pi over 3, right? It's like the derivative of 8x is 8. This is no different. The derivative of pi over 3x would just be pi over 3. What's the final step before I actually have my official slope of the tangent line?
Plug in at x equals 2.
Plug in the 2. That's right. So dy dx at x equals 2 is going to give me cosine of 2 pi over 3 and then times pi over 3. What's the cosine of 2 pi over 3? Negative 1/2. And then we multiply times that pi over 3. I'm getting negative pi over 6 for my tangent line slope. Is that making sense? So my final answer for my equation of the tangent line would be y minus root 3 over 2 equals negative pi over 6 times x minus 2. So I'm hoping that you see this. Do you see how this is just like what we did the last couple days, except now we have some composite stuff happening and we got to use the chain rule. Okay. We'll see. I don't know if we have time to look at one more. Let's at least think about it. Do you have any questions on number 2? Let me see what I want to do with this then. This one, let's do this one together real quick. We'll skip 3 for a second, and let's do 4 together. It says, find this. What is that? What is it telling you to do? Derivative with respect to x of g of x, yeah. And then it defines g of x as ln of f of x plus f of tangent of x. And f is some unknown function. We don't have a clue what it is, and that's okay. Can you see how both terms are composite? It's not just ln of x, it's ln of some other function. And it's not f of x, it's f of tangent of x. So, in the first one, which one's the bigger box? Which one's the bigger function? ln. ln of something, that's the big box, meaning that f of x is the little box. In the second term, which one's the big box? F? F of something is the big box, right? Tangent would be the little. So, as I go to try to find g prime of x for that first term, you guys remember what the derivative of ln of something is? 1 over something, right? So we're going to make this 1 over f of x. But then we've got to multiply by the derivative of the little box. What's the derivative of f? F prime. Yep. So it'd be 1 over f of x times f prime of x. And then how about that second term, the big box you guys identified as f of something? What's the derivative of f of something? F prime of something. In this case, of course, it's tangent. But then we got to multiply by the derivative of the little box. In this case, that would be? So nice. Secant squared of x. Secant squared of x. You could clean this up a little bit, but this is fine as is written. Say again?
Like, could we write the answer just like that?
Yeah. I mean, you could obviously multiply the first 2 factors together and clean it up a little bit, but otherwise, I think it looks really, really good. Okay. By the way, we'll keep doing chain rule for, I don't know, let's say the rest of the year. We'll keep doing chain rule over and over and over and over. And don't worry, it's not going away. If you would, clear off your desks, make a fort. You guys could help each other with the little fort building materials. That'd be great.